Look at section 5 of chapter 9, and so we're going to apply the same ideas but this time to volume and surface area. So we're going to find volume and surface area of three-dimensional figures. A polyhedron is the first type of three-dimensional figure we're going to talk about. A polyhedron is made up of polygons. So in simplest terms, if you think of an ice cube is going to be a polyhedron. And it's going to be comprised of, depending on your ice maker, squares or rectangles. So to develop a formula for this, it is possible to do this with your students. You're able to take and model the 1-inch square blocks, and you're going to fill up a surface with those blocks and then count them. So this is more of an activity as you're introducing this idea to students and helping them see how it connects to the real world. If I want to actually utilize the formula here, I do length times width times height. So if I don't want to fill up a container with little squares, I'm going to have to do length times width times height, which in this case is 2 times 3 times 2. So that would be 12, and we would be able to fill it with 12 blocks. Just like the area of a square was different than the area of a rectangle, the volume of a rectangular solid like a shoebox versus a cube is going to be different. Length times width times height works for rectangles. And then because in a square all sides have the same measure, we say it's going to be side cubed. So if I want to find the volume of the rectangular solid here, I could fill it up with those little blocks again. Or I could follow the formula, which is going to be a bit easier, but we still want them to connect the answer to what it is. And what they did was they gave it to me in feet. So if I wanted to know how many cubic feet it held, I would do 4 times 30 times 11. But they didn't ask me that. They asked me for cubic inches. So I have to convert every value over, or I have to convert my inches to my feet. So I'd either have to convert 2 things or 1 thing. So I'm choosing to convert 30 inches over by dividing 30 by 12. Then I can complete the multiplication and get cubic feet. So if you're finding the volume of a pool, we're going to assume the pool is probably rectangular. It's 18 feet wide by 36 feet long and has an average depth of 4 feet. Now it's asking me about gallons, and gallons are 7.848 gallons to 1 cubic foot. So if I find the volume in cubic feet by multiplying my dimensions, then I take those cubic feet and I convert them to gallons. So I know that cubic feet has to go in the denominator because it has to match up from our unit conversion alignment. And so I'm going to do 2,592 times 7.48 to get roughly 19,000 gallons. Now if I'm working with a cylinder, the volume formula is pi r squared times the height. These aren't as simple as filling them up with little square cubes or rectangles because a cylinder is going to have a curvature to it. So a great example here would be a soup can. If I have a soup can that's a right circular cylinder, it has a height of 4 inches and a radius of 1.5 inches. So here we know that we have units that are the same, so I don't need to do a unit conversion when I find the volume. But it does tell me that 1 ounce is about 1.8 cubic inches. So the simple part is finding that volume using the formula. So I'm going to do 1.5 squared times 4 times pi, which is roughly 28.3. What I need to do to find the actual ounces is I need to convert my units. Since I'm using cubic inches, the cubic inch conversion goes in the denominator, and I'm going to divide 28.3 by 1.8 to get 15.7. If I do a pyramid, pyramids are fun. Pyramid is a very not commonly used polyhedron. And this one is going to be 1/3 the area of the base times the height. So students are often going to kind of get mixed up there because they're not going to find the area of the base which is what the capital B stands for. So in this case, I have a pyramid that was built a lot of years ago, but that number is not relevant to our calculations. It has a square base that measures 230.6 meters on its side, and it is 138 meters high. So I look and I see they're both in meters, so that's a preliminary check plus. I'm so glad to see that. To find the area of the base, since it's a square, the area of a square is the side squared. So I'm going to square 230.6, and that's going to yield that 53,176.36. Then from there, I'm going to do 1/3 times that area times the height of 138.8 to get my cubic meter. Now let's look at a right circular cone. A right circular cone is similar in that it's going to be 1/3 of pi times the radius squared times height. So notice that I have another 1/3, and I have another pyramid type image because the top of it does get made up of a triangle. So in this case, I have cups attached to a water cooler. So you know the cups we're talking about. They come out and you've got a little cone that you're filling basically with nothing on top. How many ounces of water do they hold? So first I see that they're both in inches, so that means I can just get right into that formula. So I'm going to do 1/3 times pi times my radius squared times my height, which gives me 7.1 cubic inches. Now the problem is the answer I want to find is not in cubic inches. I want to know how many ounces that is. So again, I'm going to have to put that cubic inches measurement at the denominator, and I'm going to need to take that and do the conversion by dividing by 1.8. And then if I have the volume of my cone, or volume for a sphere, sorry, not a cone. If I have the volume for a sphere, this is a little bit different. A sphere, we want to make sure we show students is a basketball. Many students think a basketball is like a circle, so sometimes they're going to have some issues with visualizing a sphere as a three-dimensional object, just because in their experience they're thinking of circles. So in a sphere, there is still a center. So if you think about if you were to stick a pin into a basketball, you could actually get to the center of that basketball. And so even though it's not a circle, a sphere still has a radius measurement. And so the volume of a sphere is 4/3 pi r cubed. So if we look at an example, the Epcot ball is the most famous example of a sphere. It has a diameter of 164 feet. So to find the volume, I'm going to have to figure out, well, 164 feet is the diameter. I need the radius, so I'm going to divide it by 2. Then I'm going to plug it into the formula, and I'm able to get my answer in cubic feet. Now, surface area is going to be a similar idea to area, but this time it's an area of a surface. So it's not just one flat thing, it's multiple sides. And so a great application of this is a box. Students understand boxes. It has 6 sides, a top, a bottom, a front, back, left, and right. The way that we do surface area is we find the area of each surface and we add them together, and then we're able to get, like, if we wrapped it up with wrapping paper. So surface area is like you're wrapping the box, you're wrapping the present. It's how much that would take. So when we're doing this, we could say the top is 10 by 8, which is 80 inches squared. Now, the bottom is identical to the top in most cases, so that's also going to be 80 square inches. Next, the front side is 6 by 10, so that's 60 inches squared, and that's going to be the same as the back. And the right and the left sides have an area of 6 times 8. So here's my 6, there's my 8. That's where I'm getting these sides are 6 times 8, and then I'm going to add up all of those values together to get 376. Now, there is a formula you can utilize to do this. You can utilize this formula here. I personally find surface area easy to calculate by adding the areas of each surface, and the formulas are a bit of a struggle for me, so I utilize this for me to be able to get to an answer. Here's a reference slide for you to use. These are the surface areas of your three-dimensional shapes. If I'm finding the surface area of a cylinder, I'm going to use the previous formulas, and let's assume that the radius of a can is 1.5 inches and the height is 4. So I would simply replace that into the surface area formula to get 51.8. Now when we're dealing with the cylinder, that's a bit harder to think about the surface of each face and adding them together, which is why the formula is typically a little bit easier in that case. If I want to find the amount of building material needed, this is a very great example of surface area. If an aluminum silo is being made from a right circular cylinder with a right circular cone on top, they give me the radius and the height. They also give me the height of the cone. How many square feet of aluminum do I need? So I'm basically going to have this support structure that I'm building, and I'm going to put aluminum around the outside of it, and I'm trying to find out how much aluminum to use. So when you're teaching students this concept, I really recommend you have a diagram for every problem, because that's really important. And then for this, we are going to treat the cylinder and the cone as two separate calculations. So a cylinder with no top because the cone is sitting on top of it, and we're going to have the cone with no bottom. And so we plug into those formulas and we get our cubic feet answer.